All right, so we're going to look at implicit differentiation now. So the key is in the name here a little bit. It's when you've got a function where one variable is implicitly a function of another. So let me show you. For example, if you got given something like x equals root y. Now y is a function of x, but it's not explicitly a function of x. But you could imagine that if you did some rearrangements, that you could get y as a function of x. So we say that y is implicitly a function of x here. So what we want to do, if we wanted to differentiate something like this, we start by differentiating both sides. So you're going to get differentiating both sides with respect to x gives you ddx of x equals ddx of root y. And then what we're going to do is we're going to let u equal y to the power of a half and apply the chain rule. So let me just talk through this part because it's a bit tricky. So we're going to say u is equal to the right hand side and apply the chain rule. So we have u is equal y to the power of 1/2. So we're taking the derivative of y to the 1/2 with respect to x. Okay, but y to the 1/2 is u, so that's the same thing as taking du dx because we've let u equal y to the 1/2. Okay, and this is where it's a little bit tricky. Remember, when you usually apply the chain rule, you sort of set the inner function to be u, but now we haven't got that. We've set we've set u equal to the whole thing. So if we were to apply the chain rule though, and if you think of it as a composition of functions, where you would take du dy, so you would take, to define the derivative of, to differentiate u, you would take du dy, so you differentiate the function u with respect to y, which is basically that step of taking down a half, leaving the y there, and then putting negative 1/2 at the top. And then you multiply by the derivative of the inner function with respect to x, because remember y is implicitly a function of x. So you're going to take the derivative of the inner function, which is y, with respect to x. So you're applying the chain rule by saying, all right, du dx, the derivative of this whole thing, is equal to du dy by dy dx. And you can see how that steps out. You take the half out the front, y to the negative 1/2 multiplied by dy dx. And we end up with that situation. And then you just simplify using, it. Actually, we haven't simplified it at all. That's the same step there. And then simplify using the index laws. So you end up with this. So we know that y to the power of negative 1/2 is 1 over the square root of y. And then we've got this 1/2 factor at the front. So it's 1 over 2 root y by dy dx. And we know that the left-hand side is just equal to 1. The derivative of x with respect to x is just 1. So the left-hand side here is 1. And so now we just try and solve for dy dx. So if we isolate dy dx, you'll get 2 root y. And we have to assume that y is greater than 0 because we're taking the square root of y. So that is basically implicit differentiation. It's an interesting idea. Sometimes it's easier to implicitly differentiate rather than rearranging the function, where you might end up with something more complicated to differentiate. So we know, again, just to reiterate, that y is implicitly a function of x. So we differentiate y using the chain rule, and we can get to our answer that way. And sometimes that's a better approach. So if we just start to think about what all this means in terms of a graph, if we were to get our axes, we said that x has to be greater than 0 and y has to be greater than 0. So we're just in quadrant 1. And if I just explain what's going on here, x equals root y. Okay, you can see that this is just the graph of y equals x squared if you think of it as an explicit function of x. But, it's obviously just been rearranged, but you can clearly, hopefully, just rearrange this in your head and you would get y equals x squared. And then you can see that this here, the derivative of that is just a linear line, which is 2 root y. But again, remember y is essentially equal to x squared. So this would be 2 times the square root of x squared, which is just 2x. And from other differentiation work you've done, you know that the derivative of x squared is just 2x. But this is how we would sort of represent it using implicit differentiation, where again, we're saying that y, we know y is a function of x, but sometimes it's just easier to leave it as y rather than rearrange it into being a function of x. So hopefully that's making some sense. It can be a bit of a tricky idea. I encourage you to do lots of practice problems. Get in touch if you've got any questions, and I'll be more than happy to help you out. Good luck with everything you're doing. As always, if you found this useful, give us a thumbs up, and I'll talk to you soon.